Hi, my name is Chris Eliasmith, and I'm co-CEO of Applied Brain Research. Today I want to talk to you about our latest product, NengoEdge. The purpose of NengoEdge is to let you bring your data onto our software platform and then build low-power AI that targets edge hardware. So to give you a little bit of background on the company, we focus on time-varying data, so anything that's changing over time, be it biosignals or speech or natural language. And what we've done recently is build this product called NengoEdge, which is a tool that allows anybody to bring their data to our software platform and then build themselves a model which will run extremely efficiently at the edge and be optimized for particular pieces of hardware. In addition, we have a sort of special new kind of neural network, not to spoil the story a little bit later on, but in any case, it's called a Legendre memory unit, or LMU, and we can show that it gets state-of-the-art performance on that kind of time-varying data. And what I'm going to do today is sort of show you how these two things connect. How do we use our tool, use the LMU, approach some time-varied data, get some state-of-the-art results, and understand this from the perspective of somebody who wants to perform exactly that kind of development. So imagine that you have the following problem. You want to build a light switch which is voice-activated and voice-controlled. So you need to do things like specify particular words that you're going to use to turn the light switch on or off, maybe change the dimming settings and so on. And if you want to do that, it means you're going to be building your AI model, which is doing all this speech recognition, for a particular piece of hardware that's deployed at the edge, right, in the wall. How do you do this? Well, it's actually not really easy. Programming edge hardware is difficult, not only because you have to understand AI and the models and collect a bunch of data, but also because once you go to put it on the hardware, you're faced with some significant challenges. In particular, it's really obvious that there is a lot of fragmentation at the edge right now. So I've got a list of hardware vendors on the right. This is obviously only a partial list. And as you can see, there are many, many options when it comes to edge hardware. In addition, there are no general tools. So I can't build my model once and then say, OK, put it on the following 6 pieces of hardware so I can see how it performs across those different options. So that means for each piece of hardware you've chosen, you have to go and set up a development environment. If new hardware comes onto the scene, you have to do that again. Setting up those environments can be extremely complicated. It can take many days. And so for every piece of new hardware, you're going to have to go through this big, complicated process and make sure that you can compile your model onto that particular piece of hardware. Of course, because there's so much overhead for each piece of hardware, it means that it's difficult to compare across pieces of hardware, right? What I'd like to do is take my model and run it on a bunch of different size microcontrollers, let's say, to see how much memory do I actually need, how can I ensure that I get real-time performance and so on. But doing that is going to incur all this overhead. And furthermore, when I go to put it on the hardware, often different hardware has different statistics. And so I want to do optimization for that particular piece of hardware. So if it has more memory or less memory, my optimizations might be different. So given all of these challenges, it becomes extremely difficult and somewhat annoying, basically, to put your AI model on the edge, even if you have a nicely working AI model. So this is exactly what the purpose of our NengoEdge tool is. It's to help solve that challenge, to make it low effort to do hardware deployment. So the idea is that you essentially bring your data, you specify a model, you pick the hardware you're trying to target, and you hit the optimize button. Once you've done that, the software system goes away and does its thing. It puts it onto that particular piece of hardware, it runs it on that hardware, it collects a bunch of metrics about that particular piece of hardware, and then shows you the results. So you can do that across many different pieces of hardware and make a data-driven decision about what the right piece of hardware is for you. Once you've done that, you can simply download the model and deploy it. So the entire process is essentially the one I just summarized. I've got it diagrammed here on the right-hand side. Bring your data, define your model, determine how you're going to apply that data to the model. So what does training look like? Pick the hardware you're interested in, hit the optimize button. It'll go run, train, optimize for that real hardware. Then you can simply download your favorite one and deploy it. So this eliminates all of that overhead where you have to set up different pieces of hardware because it's all been done for you by us, sitting in the cloud behind this web interface. Now, hopefully this sounds like it's right for you, but one thing you might be wondering is, well, why would I go and use your particular software tool? Because I know I've seen similar kinds of offerings elsewhere before. To an extent, that's true. I think we have a little bit more of a focus on hardware. So being able to target many different pieces of hardware is kind of the thing that we want people to be able to do. But there's more than that. We also have our special sauce that I mentioned before. And this comes along in the form of that Legendre memory unit, or LMU. This is really a new kind of neural network, and it's not very often that a new kind of neural network comes along. So let me take a step back, dive a little bit into the theory behind the neural network and sort of explain why we get really good performance and then demonstrate that we in fact do. And again, I'm going to be focusing on speech, but in fact these results apply to many different kinds of applications. But let me start by telling you more about the Legendre memory unit. So let's start with a simple problem, the problem of trying to remember information over time. So suppose I have an incoming input signal. It looks like this gold thing I've got, this little gold squiggle. And what I really want to do is delay this gold squiggle for some length of time. So I'm going to have a system, neural network, in comes the gold signal, out comes the blue signal. That means that delay, let's call it 1 second, is memory of the input that is incorporated inside of the neural network. And interestingly, that is an infinitely difficult problem to solve. It's infinitely difficult because I haven't put any constraints on the nature of the input signal. So of course you can't solve an infinitely difficult problem with finite resources in a piece of hardware. But what we've done with the LMU is demonstrated how to find the optimal finite solution to exactly this problem of remembering information over time. So if you're processing time series data, that just intuitively means that you kind of remember what you've seen. You can get this really long context and then compute a nonlinear function of that delay, right, which of course neural networks are great at, and perform all different kinds of time series processing. So here's an example of it performing exactly this function, where in this case it's using only 6 neurons to delay this input signal for 1 second. And you can see that the delay, which is in green there, looks exactly like the original input, almost identical. Of course, there's some error because it's not perfect. And this is exactly what happens when you have finite resources for a really difficult problem. We can prove is doing as well as it could given that number of resources. Of course, if you're at the edge, being constrained to finite resources is definitely something that you're faced with. So with this kind of optimal compression, we can, as I said, take that compressed information and then put it through some nonlinearity to compute arbitrary functions of history, which of course is exactly what you're trying to do when you're doing time series processing. So on the right-hand side, I've diagrammed the Legendre memory unit, or LMU, and that linear component in the middle, that's the optimized part. So the A and B matrices, those are weights, and you don't change those. You don't need to learn those. They're optimal already. All the rest of the weights that you see here, you can learn just like you would using normal backpropagation. Put it through some nonlinearity, so something like ReLU or what have you, and then compute whatever function you're interested in computing. So the special thing about this is that we can prove any kind of performance guarantees. That's very unusual for neural networks. And this is really why we call it a new kind of neural network. That kind of thing isn't true of standard time series processing networks like LSTMs or transformers. It's really only true of the LMU. And perhaps unsurprisingly, but in fact we didn't know until we tried, this has demonstrated that the LMU outperforms all of those kinds of networks when it comes to time series processing. So let me give you a couple of examples. Unfortunately, I'm not going to go into all that data. But let me start by just looking at what the LMU has been optimized for, and that is remembering information over time. So here in the graph on the left-hand side, we're comparing an LSTM to an LMU, where we're giving an input signal. You can think of this like the gold signal, and it's trying to remember it for some length of time. Now what we're doing is we're sampling that input signal more and more finely. And as you sample it more and more finely, that means that the number of samples you have to remember as a network is going up and up. And unsurprisingly, we see that the LSTM gets worse and worse because it's trying to remember more and more information. Of course, in contrast, the LMU is actually getting better, or maybe not of course, but perhaps surprisingly, in contrast, the LMU is getting better. And this is because the more samples you have, the more accurately it is approximating that continuous time problem, which is really the one that the LMU is optimized for. In any case, this results in us on this task being able to say that the LMU is about 1,000,000 times more accurate. So if you look at the left-hand side, the mean squared error goes down by 10 to the 6. At the same time, it's using 80 times fewer parameters, i.e. only 500 versus 41,000 for the LSTM, and it's remembering 10,000 times more data. So it has 10,000 times more time points that are stored in its memory compared to an LSTM. Now, perhaps it's not too surprising that the LMU is outperforming an LSTM here, because this is literally what the LMU is optimal for. Nevertheless, we can turn with that LMU that I showed on the previous slide to standard machine learning benchmarks. And so here's one. This is called permuted sequential MNIST. So what you do is you take an MNIST digit, you take each of those pixels and provide it to the neural network one at a time. So you basically turn it into a time series after randomly permuting them. And this has become a standard benchmark for all kinds of new recurrent neural networks that people have suggested. And so it was very natural for us to run the LMU on this. And as you can see in the chart at the right, there's a whole ton of different kinds of RNNs people have proposed, but the LMU is doing the best out of all of these. Furthermore, it's using 60% fewer parameters than any of the other ones in that chart. And in fact, our latest LMU has set new state-of-the-art even above our first initial attempts with the LMU, and we're up really high now, around 98.5% accuracy. And in fact, we've taken the LMU and set state-of-the-art in many, many different benchmarks. I've got a sort of partial list down at the bottom left there, and we encourage people to take it and try it on whatever benchmark they're interested in. However, this isn't really an application, right? It's not practically useful to be solving PSMNIS. Nobody cares if you can recognize digits that have been strung out as a time series. So what I'm going to turn to now is looking at what happens when we apply the LMU to speech processing. So what we did is we took the standard speech benchmark, which is speech commands v2. We built LMUs of many different sizes in order to compare across some of the solutions that people have proposed. And we came up with the following graph. Now, conveniently, Google, who really supports the use of speech commands, had published a paper last year where they took all of the best work people had done in other labs. They had optimized it for streaming, i.e. actually deployable cases, so you don't have big delays. You're just processing the audio data as it comes in constantly. And they published their results, and those are all shown in the sort of top left corner of this graph. And I should note that your accuracy is going up on the y-axis, and the size of your model is going down on the x-axis. So what LMU1 is showing that we can match the highest accuracy of any of the optimized solutions from Google while being a smaller model, which is great. That means your power is going to be smaller, or you can do more AI on the same size of microcontroller or what other edge device you're using. And then the rest of these LMUs are showing basically that you have this kind of Pareto optimal front, where for any combination of accuracy and size, LMUs are doing better than other solutions that people have proposed. And this is what lets us make the claim at the bottom of this slide that the LMU gives the world's most power-efficient streaming keyword spotting models. Now, from a NengoEdge perspective, this is the very first thing that I think is absolutely the easiest to do on NengoEdge. So if you have any kind of keyword spotting problem at all, this is going to work for you. We've taken these results and we've scaled them up. We've also applied these results to natural language processing, demonstrating that the LMU very significantly outscales transformers. So it's at least as much better than transformers as transformers are compared to LSTMs. So there's a lot more that you can do with LMUs, but for the purposes of this presentation, just to keep things on time and short, here is a really easy, direct, and useful application of the LMU to speech processing. So what I'm going to do now is run a quick video that shows you exactly what it's like to use the NengoEdge interface.
All you need is an idea, and NengoEdge takes care of the rest. The next step is to head over to edge.nengo.ai and make your idea a reality. Once you're logged in, a tour will show you everything you need to know, from datasets and network configurations to training and deployment, but we'll skip it for now and get right into it. Let's say I want to make a hands-free, voice-controlled fan for my workstation so I can stay cool and focused. The first thing I'll do is select a dataset. I have a dataset with the commands up, down, on, and off on my hard drive, which I'll quickly upload to NengoEdge using the Upload New Data button. Once this is uploaded, I'll create a name dataset with this new data for training a network. We'll give it a name, select our keywords. There are also some dataset properties available here, but the defaults work well for most applications. Now we can see our new dataset, and in fact we didn't need to upload our own data because the speech commands dataset available through NengoEdge already has these keywords. In any case, we'll head back to the runs page and start training. First, we'll create our new project, and next we'll create a specific run using our desired configuration. Just choose the desired hardware. The most recent dataset is automatically selected, but you could choose a different one here if you like. Since we're doing a new project, we don't have any initial weights, but if you're fine-tuning, you can start with some pre-trained weights to cut down on training time. Next, we'll choose our neural network architecture from a drop-down list of predefined networks that are known to have excellent performance on time series data like speech, using our unique Legendre memory units. The default training parameters are known to provide excellent performance, so the only change I'll make is to enable our proprietary hardware-aware training to more closely match deployment. Next, we have some more dataset properties, but again, the defaults are good, so we'll leave them as is. And that's it. Now we click Optimize and let NengoEdge take care of the rest. This brings us to the progress page where we can see our application training in real time. We don't need to sit here though. We can create new datasets or new runs and come back and see progress anytime with NengoEdge working in the background. Now that our training is complete, we can look at results and begin deployment. Here we can see a breakdown in performance with accuracy and streaming metrics, as well as speed and size. But for now, let's move on to testing and deployment. We can record live audio to test the network by clicking Start Recording. Down. Now send this clip to the device to test inference. Once you're satisfied with the performance, you can download the model as just the weights, or directly download the compiled binary application ready to be deployed. Up, down, on, off. And there you have it. We went from an idea to an edge device with just a few clicks. I've taken the compiled binary from NengoEdge and loaded it onto my personal device, where it's classifying audio in real time. Now I can connect this to my fan and control it hands-free.
So that video should give you a good overview of what happens when you come to NengoEdge with a particular application. We currently have several alpha users using NengoEdge. Some of them are doing things like keyword spottings, others are doing audio scene recognition, biosignals processing, and so on. If you have any problem like this, please drop us a line and we'll figure out if we can get you on NengoEdge using it right away, because we are looking for more alpha users. Thanks for your time.